Hello again. In this video, we're going to look at a famous related rate problem about a ladder, where the top of the ladder slips down the wall as the foot of the ladder moves. So let's go and read the problem. A 3-meter ladder stands against a high wall. The foot of the ladder moves outward at a constant speed of 0.1 meters per second. When the foot is 1 meter from the wall, how fast is the top of the ladder falling? What about when the foot is 2 meters from the wall? Okay, here's a side view of the situation. We're going to let x be the distance here on the ground from the base of the wall, and y be this vertical distance, or the top vertical distance from the base of the wall in meters. Oh, and I forgot to say in meters here. The distance on the ground, we can say in meters. And what we want to know is how fast is the y changing with respect to time, not with respect to x, and how it's related to how fast this x distance is changing, because they're giving us that x distance. So if you see here, the foot of the ladder moves outward at a constant speed of 0.1 meters per second. So that would be that x distance. So they're giving us, we can write that down, that dx dt, because it's within meters per second, and it's moving outward, so it's going to be positive meters per second. We do have that. And we're looking for, again, how fast is the top of the ladder falling. So given dx dt, we want to find dy dt. By the way, let's do the first part. When the foot of the ladder is 1 meter away from the wall. So I can write that. When x equals 1 meter. So we need to come up with our own equation here. And I know this is a triangle. This is a right triangle. We know that the ladder is 3 meters high, or 3 meters long. So we can know the Pythagorean theorem. So we can say that x squared plus y squared, we know, is 3 squared, which is 9. So again, if we find dy dx, which is what we did in the past, it's not going to help us because we don't know. First of all, we want to find dy dt, and we're giving dx dt. So what I'm going to do is do just that. I'm going to take the derivative with respect to t to both sides. So now, both of these would be using the chain rule. 2x would be the derivative of the first one, and if with respect to x, we just leave it as 2x, but now it's with respect to t, so I'm going to multiply this by dx dt, the derivative of the inside. The same thing with this, 2y, we have to multiply that by a dy dt, and the derivative of a constant is still 0. So then we can plug in what we have here. We know the x is 1, we know the dx dt. The problem is we do not know y. But at that instant, we can do a little picture of just this one, the moment that it's 1. So this ladder is O is 3, and it's being pulled out, so it's different at different x's, right, as it's being pulled out as time goes along. But at the moment that this is 1, we can actually find this. We could find that y by saying 1 squared plus y squared is 3 squared. And you can get that y squared equals 8, or y is equal to the square root of 8. It's a distance, so you do not need that negative. And that we can plug in to that y here. So you do need to be careful and not plug this in right away, because dx dt is changing, so the x is not a constant. So notice how I put this on the side here. I didn't plug in the 1 here and then take the derivative. I did on the side, and then right when we're plugging in, just to use that to find that one value. So now we can plug everything in. 2 times 1 dx dt, they're giving us is 0.1, to the square root of the y is the square root of 8 dy dt is equal to 0. If we solve for dy dt, we get the answer. So I'm just going to multiply this, bring this over, and then divide by the 2 square root, which turns out to be negative 0.035, and that would also be the y is in meters per second. So what does that mean? Let's go back and look at our picture again. That means that as x is being slipping down and getting larger, the y is getting smaller at a little bit less of a speed. The absolute value is 0.03 versus 0.1, and it's doing a little bit slower than how fast the x is being pulled out. In general, in fact, if we just look at this equation here, we can actually solve for dy dt by subtracting this term and then dividing both sides by 2y, and the 2's cancel. So you can see here that when x, this foot, increases, the y decreases, so the numerator is getting larger and the denominator is getting smaller. So that, and the dx dt is a constant, so that tells us that the magnitude of dy dt is increasing as x is getting larger. To see that, let's answer the second part of the question. What about when the foot is 2 meters from the wall? So again, now it's 2 meters, so we need a new picture here. It's a little farther out. This is still 3. Now we're looking for a new y. So we have x, 2 squared, plus y squared equals 3 squared. So solving for that, we get y squared equals 5, or square root of 5. So now I have this already solved for. I don't have to solve it every time. That's a dt there. We can have the x is 2. This is when x was 2. And the y, that's negative. We found a square root of 5. The dx dt is still moving at a constant speed of 0.1. So what is that going to be? Multiplying all that out, you get negative 0.089. If you look at the magnitude of that, it is a little bit larger. So that's the answer for the second question and the answer for the first. Hope that helps.